Okay, so we're going to finish up the PhET fission activity. This is part 3. We're looking at the nuclear reactor. So you can get on to the simulation again. Nuclear reactor tab is this tab right here. And it brings up something that looks like this. You'll probably have the control rods all the way up in place. This is what a nuclear reactor actually looks like. This is a picture of a nuclear reactor at Penn State University. A lot of college campuses have a very small nuclear reactor on them. It's a pretty common thing. They're fairly safe. I mean, we think about the disasters of nuclear reactors, but it's very, very uncommon. So let's take a look at this. Hello, my cat Minnie is back again. All right, so when you're looking at this, you can adjust the control rods in and out, and we're going to think about what the control rods do to make this happen. So I'm just going to experiment for a second. I'm going to fire some neutrons. We're going to look and see what happens. Maybe keep thinking about it. As you notice that it's getting a darker red or orange, that's really, really bad when that happens. We don't want the temperature to get up too high, because then that is when it goes into a nuclear meltdown, which is the kind of thing you heard happen at the Fukushima reactor, the kind of thing that happened at Chernobyl. So those are bad things that happened, kind of thing that happened at 3 Mile Island in the United States, or almost happened. So with these, what we're doing is we're looking at the function of the control rods. So now if I fire the neutrons again, but I've got the control rods mostly in, think about what happens. Notice that so think about what you notice with that. If I've got the control rods all the way in. One thing I will talk about with this is thinking about designs for nuclear reactors. Some nuclear reactors have control rods that insert from the bottom. In the United States, nuclear reactors have control rods that insert from the top. And the reason that the United States nuclear reactors have that is that those rods can, pardon me, that those rods, if we lose power to it, those rods will just fall into place. Gravity will get them into place. Whereas if you have to have power to get them up into place from the bottom, then that's an additional problem that could happen. So, looking at these questions. Yes, Katie? So, I want you to think about a couple of things. Watch the fission reactions. What happens if the neutrons hit another nucleus? What happens if the neutrons hit a control rod? Think about what might the control rods contain. Think about what you saw in the last fission experiment, or in the chain reaction part. What might have a similar reaction to what happens with the control rods? Now, the problem with this is really, really small to see. So I often have problems thinking about it. So think about when the neutrons, you might only kind of barely see the neutrons hit the control rods down here. You'll notice that they don't really do anything after that. When they hit a nucleus, they cause the nucleus to explode, right? To fission, give off energy. The other question was asking about these two bar graphs over here, the power output and the energy produced. So if we think about that, the power output, you'll notice it's in joules per second. So this is a measurement of how much energy is being produced at any one time. So right now when there's a lot of them going off, there's a lot more joules per second. And you'll notice when there's fewer of them going off, this number goes down. The energy produced is in joules. So this is just the total amount of energy that gets produced in the whole thing. So there's that. So you're going to think about comparing the chain reaction that occurs when the control rods are inserted further in and when they're pulled almost all the way out. Thinking about why there are the control rods there. I kind of already gave you a hint about that a little bit, so think about it. 2 to 3 things about the control rods you would like to know more about in order to understand how they work. So this is kind of an open-ended question. I want you to just think about what would you like to know more about the control rods. And then I want you to think about the similarities and differences between a nuclear reactor and a nuclear bomb. And alright, I'm running low on power, so I'm going to pause. Logged in time, no losing videos today. That's a plus. Alright, there's another video you're going to watch to see this. I'm going to put it next in the playlist for this, so you can watch that, describe how energy from a nuclear reactor turns into electrical energy that we use. So thinking about that. And then finally, I'm going to also go through part 3 and, well, I just went through part 3. I'm going to go through part 4 as well, give you a couple of things. So thinking about nuclear fission, what did we see? Is that the splitting or the combining of an atom? And is it stable or unstable atoms that do that? What do we refer an unstable atom? Is it radioactive or is it an isotope? For the fission of uranium, think about when we looked at fission. Did it start as mostly stable or unstable? And then it gets hit by what? A proton, neutron, or electron. During the nuclear reaction, what does the atom particle cause the big atom to now be more stable or more unstable? And at the end, there are two smaller, more stable or more unstable atoms. Which do you think? Nuclear fission releases a small, large, or massive amount of energy. One thing I'm going to clue you in on here, this came out, and I apologize it came out this way. You're going to want to shrink this down so you can see everything in this equation. It's like the one I wrote in part 1, and that's something you want to think about. This simulation down here only has one neutron shown because I didn't realize that the image was not correct when I sent it out. So the stuff on the left side, is that the reactants or the products? And the right, reactants or products. The mass of the reactants, is it going to be equal to, greater than, or less than the mass of the products? So if we think about the mass, we've got 92 plus 141 plus 1 plus 1 plus 1, all of the mass numbers on this side. And then 235 plus 1, all the mass numbers on this side. So think about that. Proton amount, and in the reactants, proton amount in the products. So on this side we have 92 protons and 0 protons. In this side we have 36 plus 56 plus 0 plus 0 plus 0. Think about adding up the total mass that we talked about earlier. The numbers at the top. And then why do fission nuclear reactors release a massive amount of energy? Because they cause a blank between many atoms of uranium. I'll give you a hint. That is a 2-word answer that you will find earlier on this worksheet. I think that's about all I've got to say. I'm not going to talk about that fission screencast because I'm putting these videos up so you have a better chance to, or a little bit more to see to understand them. And that's all I've got to say for part 3 and 4.